introduce you a little bit more about deep neural networks, specifically just around different architecture. Guys, it has been a long way, right? So you guys went all the way from, learning about Python in the first week, preparing and getting your data, right, for your project first week. And second week, what we did was actually, we learned about data analysis, we learned about, machine learning, right? We learned about data visualization. And then we also got our deep neural network trained. However, I think it's only until yesterday where we started learning about how deep neural network works. Today, what we're going to do is actually a computer vision class, which is really about understanding how YOLO would work. Okay. So right now, I'm just going to give you a few, maybe two, newer architecture where you probably haven't seen them before. This is really about, we arrange these neurons into different, basically, shapes, different layers, okay? So here, what you're looking at is basically a whole bunch of different neural networks, right? So you can see, the simplest one is this thing called a perceptron, right? Which is basically, you have these input cells. So you can see the input cells, there are these yellow cells, right? And then the output cell are those red cells, okay? So for this simple perceptron, right, it's literally just like, two input cell and one output cell. Can someone describe to me for this perceptron? Do you guys know what kind of computation is being done in this network? First of all, what's a neuron?
The neuron would connect the input and output.
Right. And neuron has a value, right? Okay. And what are those connections, what they are called? Weights, right? They're called weights, right? So all we're doing right now here, right, is basically, right, take a linear combination of these two values, right? Linear combinations of these two values, and then passing through an activation function. That's your output, right? That's what perceptron is. And then we also learned a little bit about these feed-forward networks, right? Pretty simple as well. The only thing that's, slightly different is that they have these hidden cells, right? So that is, between the input cell and the output cell, there are these hidden cells. And then you have these deep feed-forward network, right? So sort of like, you have multiple these hidden layers, right? So usually once you have three of these layers, right, you can call them like deep neural network. And in this case, we have 4 layers, right? So we're going to call that deep feed-forward network. So there's a whole bunch of other, interesting stuff here, which is, for example, we have these like blue cells now. And these blue cells, not only, for example, they take inputs, right, from, the previous layer, but they also take inputs from themselves. You see that little circle, circle on top of it, right? So these are recurrent cells, okay? These are recurrent cells. What we're gonna do today is really talk about the convolution networks, right? And it has very much to do with computer vision. So convolution, right? Convolution is very simple. It involves these inputs. So you can imagine the input would be, for example, a picture. And the kernel, or you can call it a filter, right, is basically you take kernel, right, and you map it to this input. And you're doing element by element multiplication. In this case, because all the input cells, right, input values, they're 0, right? So it really doesn't matter what the kernel is. The output value is going to be 0. And then what are we going to do, depending on how we're going to move the kernel, we call that stride size. So we put this kernel like one more pixel, right? So in this case, what we're doing is we move the kernel like right here. Can anybody tell me why in this case the output is 3?
When you do the multiplication, it would be like 0 times 0 plus 0 times 1 plus 0 times 2 plus 1 times 3.
Yep, exactly, right? 0 times 0, which is 0. 0 times 1, which is 0. 0 times 2 is 0. 1 times 3 is 3, right? Add all that together, you got 3. Very good. Basically, this is, stride equal to 1, right? So the first pixel is right here. Second pixel is right here. Third pixel is like that. And fourth pixel is like this. You see that? Which is why, you take this, 5 kind of by 5, you put a stride equal to 1, and you got 4 pixels here, right? You got these 4 pixels. Once you got those 4 pixels, then what you do is you move downwards, right? So what you do is you move right here, right? You get a 1 pixel, right? another one, right? Another one, and finally the fourth one. Okay, you see that? And you can move it down by another pixel, which is why you can create these guys. Do you see that? Okay, how many of you understand what the convolution is now? Give me thumbs up, thumbs down, in the middle, again, what we see is this, 3 beautiful corgi running around, right? I have a pretty big dog, maybe not big, but just like medium size, but her legs are, but these corgis they're beautiful. At least that's the thought I had in my mind. But you know what? The computers, they don't see any of these, right? What they see is pixels, right? All these different numbers and pixels. Let me ask you guys a question. Why do we use these convolutional neural networks? They use those filters, apply one by another, and then we get, another picture. Why do we do that?
Is it to like sort of blur the image so that it's easier to just see the shapes and outlines rather than focusing on all the little details?
Yeah, exactly, right? So you are basically trying to extract, for example, outlines or, directions from these pictures. Yes. And one of the reasons why we're using convolution, when you think about it, hey, look, instead of like having every single neuron, right, connecting to every single pixel, that would be a humongous kind of network, right? When you think about it, this picture here could be, I don't know, 1,000 pixel by 1,000 pixel, right? So all the neurons that we need for the input would be what? 1,000 times 1,000? That's a mini, right? And then you're gonna have 3 different channels. So that's 3 mini, these input cells, right? And if those 3 mini input cells, they're all connected, maybe to some network like, another 3 mini like intermediate neurons, that's a lot of connections. That's a lot of connections. Whereas we know in these pictures, pixels around these regions, right, they are related. They are related, right? Because chances are they just represent, a piece of grass here. Or maybe, pixels on this beautiful corgi, right? These are related, right? So why not take advantage of the correlation, the spatial correlations of these pixels and use basic a filter and move around and extract those features, right? Basically, we treat one patch of these guys as a unit and extract something out of it, right? So the reason, it's not, for example, we can use a deep forward network to do computer vision. We can, of course we can. That's like the ultimate network, right? It's connected to everything. It should be great. But in reality is the fully connected network has so many parameters, it's very hard to train. So as a result, what we're gonna do first is basically take a convolutional neural network to extract features first. You see that? And chances are, you can use stride size differently, maybe the size of filters differently to really reduce the dimension, okay? To really reduce the dimension. So that's the reason why we're using convolutional neural network. The other thing that we talked about a little bit is basically max pooling, right? Max pooling. Max pooling is also something used in conjunction with the convolutional neural network. And max pooling, the way we do it, right, is just say, input, you have these 4x4, right, matrix. And then the max pooling, if you use a 2x2 max pool, is basically you take the 2x2, right, take the 2x2, and you just ask what's the max pixel here? Which pixel has the max value and extract that. So in this case, 20, so extract like 20 right here. And then in this case, we have stride distance equal to 2 now. If stride distance equal to 1, you would do this, right? You got 20, and then you do this one, you put it, you mask on this one, you would get 30, and then you put a mask on this one, you get 30 again, okay? So that's stride distance equal to 1. But for stride distance equal to 2, right, then you only have these guys, right? You got 20 here, and you move by 2 pixels, right? Move by 2 pixels, and now you're looking at these guys, okay? And therefore, right, this is, the first element is 20, the second element is 30, as illustrated here. Then move downwards, right? We got 1, 1, 2, move another 2 pixels over, you got 37, okay? So that's max pooling. Why do we use max pooling?
Is it faster because you're just looking for the max instead of doing the calculation?
Well, you still do the calculation, but there's a slightly different reason. Guys, look at the dimension, how much we reduced, right? This is, all the way from 4x4. Now we go to 2x2 now, right? We drastically reduced that dimension. At the same time, we preserved maybe the strongest signal, okay? So it's really using the max pointing to preserve the strongest signal. That's what that is. Yesterday, right, you guys worked at a problem where you have these handwritten digits, right? And you were able to construct a neural network, and you were able to essentially use that neural network to classify each picture, right? Why do I say it's a classification problem? So what's the difference between classification and regression?
Classification has like discrete outcomes, and then regression has like continuous outcomes.
That's right. That's exactly right, right? It's classification because you only have 10 digits, right? They're discrete numbers, right? They're discrete classes. Like what we did, for example, rotten versus not rotten, right? By itself, that's a classification problem, okay? And the network you built is very similar to this, right? It's very similar to this. You basically have this image here, right? Which are pixels. And we learned that these pixels, there are maybe 3 channels, because not only they have an X and Y, but there are also color space, RGB. And then you will see basically you did 2 layers of these units, layers of these units. First layer, you do the convolution, right? You do the filtering. Second layer, you do the max pointing, really reduce that dimension, right? And you have this times 2, okay? Trying to extract more feature out of it. And then what do we do is you have the fully connected layer right afterwards. How many of you remember your code? Do you guys remember your code where you were building these guys twice before you do fully connected network? And then you can do the prediction, right? You can do the prediction. The really important takeaway understanding is the following. That is, when you are using the convolutional layer to apply filters and max pointing, and then you get to the max pointing, what you're trying to do here is you're trying to extract features, right? Extract features. The way to think about it is almost like, as if you apply different filters to this image, and each filter, right, they might be responsible to extract certain features out of the image. It could be maybe one filter is really great to extract round objects. So you apply that filter everywhere, and you're trying to extract, where you have round objects. And then maybe you have another filter, that filter's job is maybe to extract, maybe pointy objects, right? So you just apply that filter everywhere and you try to extract, where do you have pointy objects? So maybe, at the end, what you're gonna discover, maybe you have this, this guy here, right? That's really about the round objects. Maybe, this neuron here is really about the pointy objects. So as you can see here, these filters, they're extracting features. And then we use fully connected network. Can someone maybe take a wild guess why we are using fully connected network? And after we know this is round object and pointy object, and then we can predict, this is a bird?
Is it so that you can make a more accurate calculation or prediction on the problem?
Yes, we're making a calculation, we're making a prediction, but what I'm asking is, why do we use fully connected network here?
It's because once you've reduced the image down enough, it's more practical to use like fully connected layers.
That's one of the reasons. That's actually one of the biggest reasons, right? You reduce the dimension so much, now you can actually use fully connected network to do things. But the other thing here, right? What a fully connected network is really good at is really combining these different features for different things, right? So here it just says, maybe when the round object and pointy object, you have the round object here and pointy object here, that might be a bird, okay? It's literally just like looking at these round objects and pointy object, if it's going like this, that's maybe not a bird. Maybe it's like this, that's a bird. You're basically trying to combine these different things together to make predictions, okay? So again, right, you take this image, you extract features first, and here you're combining features to make predictions. So we're gonna see these kind of network happening over and over and over again in computer vision.